example. Here, let's look at a very simple example. For convenience, we just use 3-digit data, okay, like this. That's the data we have. So we apply the counting sort 3 times, digit by digit, from least significant digit to the most significant digit. Okay. The first time, let's apply it on the least significant digit, the counting sort. Okay. So we ignore other digits, or we treat other digits as the satellite data. Remember the satellite data, the concept I gave you before, right? Now the satellite data, this concept is important, right? So you really need to carry the satellite data. Here, so it's a good example to explain the usage of the satellite data. Yeah. So now, after the counting sort on the least significant digit, so we get it sorted in ascending order like that. Okay. Next, we need to apply on the second digit, also counting sort. Okay. Then the first digit and the last digit we treat as satellite data. Okay, so we carry the satellite data in our sorting. We just ignore those digits. So we, focus on the middle digit, do the sorting, but carrying the satellite data. Yeah. After we do that, we get this already sorted. Then let's try to examine what we have here. If you look at with the same middle digit 2, it is sorted, right? 0, 9 in ascending order. With the same digit 3, 9, 6 sorted, right? With the same digit 5, the order is preserved. That's what we call a local order preservation. That is the property we need. That is the stable algorithm can give us. Okay? Yeah. So that's why it's so important. We need to study all the details we need to get to this point. All right. So then we are comfortable about our method. Yeah. Order preserved. Actually, local order, right? More specifically, more precisely, local order preserved. All right. The last time we apply the counting sort on the most significant digit and then get it sorted, then the whole array sorted. Yeah, because with the same digit, it is sorted, same digit in order, and so on. If a different digit, the most significant already is enough to determine the order. So we don't need to worry about, we don't need to look at other digits, right? Here, we're based on a dictionary order, right? Look up words in a dictionary. So the dictionary order, dictionary. Yeah, dictionary order. Yeah, anyway. Dictionary order. Yeah. We use the dictionary order. Yeah. So now I think you should be convinced that this algorithm really works. Okay, the radix sort. Yeah. Next, further generalization, the idea of the counting sort. Yeah. So why the array of integers can be sorted? We want to see what's the reason behind it. So we try to summarize a little bit. Yeah. Because after we learn this algorithm, we want to summarize the main points we want to have. The array elements are arranged based on their values. So we know, yeah, that's the sorting. Yeah. Since the array values are integers, they are already in order based on their values. Okay. Here, the essence is array elements are arranged in ordered location. Here we have this ordered locations. Values and locations. Values and locations. These are two different concepts, right? Array values. Integer locations. There are two different concepts. But for our integer data, they can be matched seamlessly, right? But for other data types, these two things cannot be matched well. Values and the locations. Okay? Yeah. Because when we see the value 7, we can, we know this number corresponds to that location. Okay? Location 7. Yeah. So there is a location we can put in that location, right? Look at the counting sorter. We try to put in a location, right? Location. Right? But for non-integer data, you don't have this property. Okay? For 0.3758, where is the location you put? How many locations do you need to place the data like that? Too complicated. So we don't try to do it in that way. We don't try to use the location way to handle that. But with the integer data, in certain range, we can use the location way to arrange the data. So that's the main difference. Okay? All right. Row of integers. Integers correspond to ordered locations. So we emphasize this point again and again. Okay? Yeah. Why integers? We can extend it a little bit. Okay? If some data types have the similar properties, we can use this idea. Yeah. If we have ordered locations that are related to the values, we can use the idea for non-integer data. Yeah. Example is strings. We can apply radix sort on strings, right? Yeah, exactly the same idea. Okay? When we have strings, the concept of digit is slightly different. The concept of digit, okay? For English letters A through Z, the digit, the concept of digit, you have 26 digits, right? Yeah. If you have more characters, you have more digits, but you can use the same idea here. No. That's the generalization. Yeah. At the end, I want to complete this topic. So this is the last slide of this topic. So at the end, I want to give you a very interesting example to show you the power of this method. This method is very powerful. The power of this method. Okay. Show how to sort an integer array with n elements in the range. We have a range, but the range is from 0 to n cubed minus 1. Remember, it does not satisfy the counting sort requirement. Counting sort requirement is big O of n, right? The range. Here, the range is big O of n cubed. Big O of n cubed. That's the range. How can we sort it in big O of n time? Yeah. So that looks not that easy, but we have the idea of the radix sort. Can we use the radix sort idea to solve this problem? So let's look at this. All right. The key question, how to view the range from 0 to n cubed minus 1. Why minus 1 is so important here, right? Why minus 1 is so important? Right? Yeah, but here, from the structure point of view, minus 1 is important. Structure. There is a structure here. From the value point of view, -1 is not that important. But from the structure point of view, the -1 is important. Okay. All right. Let's recall the number representation in digits, our general representation formula for base D number. So any base D number we can write in this way. All right. And here, the condition, we have this condition. We have this condition. All right? Yeah. But now we want to estimate the range. So here, for the, here, this D digit, general digit, this D can be any positive integer, right? Any positive integer can be used as a base D here, right? So can we choose a special D equals n? We choose D equals n. How about that? That very special case. In that special case, now let's consider any m in the range, in this range. Yeah, because that's the condition we are given in that range. Any m in that range, how many digits do we need using the base n representation? How many digits do we need using base n representation? Can you get that? Abstraction? Here we do abstraction. Yeah, the digit. The base is n. So we do some abstraction. Okay. How many digits do we need to represent a number in this range? Okay, that's the key step. So let's represent it. The general expression here, let's consider this representation. We use 3 digits, B0, B1, and B2. 3 digits. What is the largest number we can represent using 3 digits in base n? Base n. Okay, yeah. So here, because each B, B0, B1, B2, less than or equal to n minus 1, right? It cannot be n. The largest possible digit is n minus 1, right? So let's use the largest possible digit value here. We get this one. What is this number? Do you know that? What is this number? N cubed minus 1. Because n cubed minus 1 equals, do you know this formula? N squared plus n plus 1. Do you know this formula? Here we use this formula, right? Remember, I give you AR minus BR formula before, right? Here we use A cubed minus B cubed. That formula here. Okay? Yeah. Now you understand why we are given n minus 1 here, n cubed minus 1 here. That's why I say the structural point of view, it is important. If you don't have this minus 1, how do you get this structure? How do you get this structure? Right? So, yeah. So at this point, after this analysis, we can comfortably write m as this new format. 3-digit representation in base n number. After that, can we apply the radix sort 3 times, the first time, second time, the third time? Oh, sorry. Here, I noticed something wrong here, right? Although the importance is not that big, it should be B2, B1, B0, not the other way, not that way, okay? So this way is correct, yeah. But we just apply first time counting sort, second time counting sort, third time counting sort. Each time the counting sort, because the range is n, so each time bigger of n, and we do three times bigger of n, still bigger of n, right? Okay, that's how we get this. Okay, so that using that way, we solve the problem. Okay, yeah, we solve the problem. Yeah, all right. Okay, all right. So we complete this radix sort topic. Next, I will use 2 videos to solve that string matching problem. So today we will have total 5 videos. All right, so let's stop here.